Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Sami Afan Dumawan Ishar. My student ID is 2023457982. And today, this is our presentation from Group 18, Composite Armor, Military and Law Enforcement Protection. So let's introduce ourselves. Here is all of our group members. A composite material is a combination of two materials with different physical and chemical properties. These composite materials, are usually superior than those of their own individual components. This is why composite materials are widely used, especially in military and law enforcement. In this presentation, we are going to discuss more about it. Here is our topic overview of our presentation. Firstly, we are going to talk about background and history. When did the military use composite materials? Secondly, application and examples of how these composite materials helps the military. Thirdly, we are going to talk about benefits and advantages, why these composite materials are more used than other types of materials. And lastly, challenges and limitations. What are the technical and technological challenges in advancing composite material research? And now, after this slide, we are going to talk about background and history of composite materials.
Now we will talk about background and history for composite armor. So in early armor phase, protection almost relied on metal, mainly steel. During World War I and World War II, tank, military vehicle and protective shields depended on thick homogeneous steel plates. The main idea was simple. The thicker the metal, the stronger the protection. However, this detect a serious drawback, which is heavy, high fuel consumption and difficult to transport and deploy. And moved to the World War II. From 1950 to 1970, weapon technology evolved rapidly, such as armor-piercing bullets, shaped charges, higher velocity projectile, and explosive, producing higher energy fragment. This triggered the search for new material with better strength to weight ratio. After that, the composite armor was born. Research in material introduced a new concept. Instead of we relying on one strong material, engineers could combine multiple material, each providing different protection function. The key idea was like we use ceramic layer to break and blunt the projectile, and then other than that, composite backing such as Kevlar or polymer laminates to absorb impact energy. This made armor lighter and stronger and more efficient. Next is Kevlar and fiber reinforced armor. In 1970, DuPont introduced Kevlar. Kevlar is a high synthetic fiber. Kevlar revolutionized body armor. The reason why Kevlar was groundbreaking is lightweight, flexible, high tensile strength, and capable to absorb large amount of energy. Now we move to modern military composite armor. During Cold War, country began to develop the composite armor for tanks, such as British Challenger tank, American M1 Abrams tank, and certain NATO armored vehicle. This armor used ceramic tiles sandwich between metallic and composite layer. This offering superior protection against both kinetic penetrator and explosive warheads. This proves that composite armor was not only for soldier, but also for large-scale armor vehicle. And lastly is recent development. Modern composite armor has continued to evolve with advancement in nanomaterial, ultra-high molecular weight polyethylene UHM WPE or Dyneema, graphene research, smart armor with sensor, improved ceramic technology, and lightweight ballistic composites. This improvement address modern battlefield needs, countering threats such as IED fragment, armor-piercing round, and high-speed projectile. There is so many application composite armor in army, which is body armor, military vehicle, cockpit area, tactical shield, and bomb disposal unit.
Here are the examples of composite armor that has been used in military. First one is Chopam composite armor M1 Abrams tank. Chopam armor is a well-known composite armor system used on the M1 Abrams main battle tank. It consists of multiple layers of ceramic tiles, metal plates, and a composite backing material. Each layers plays their main role, which is the ceramic layers shatters incoming kinetic penetrators or shape charges, while the composite and metal layers absorb and dissipate the remaining energy. The challenge faces from them is high weight due to multiple protective layers, and complex manufacturing and strict secrecy, limited testing, transparency. So how they overcome this challenge? First, optimization of layer thickness and material placement. Second, later visions, incorporated depleted uranium layers, improving protection without a proportional increase in size. Lastly, modular design allow upgrades without redesigning the entire vehicle. Next is composite body armor for law enforcement. Modern law enforcement body armor use aramid fibers or known as Kevlar, UHMWPE, ceramics, and polymer composites. Some systems integrate shear thickening fluids which remain flexible during normal use but stiffen instantly after ballistic impact. So the challenge they face is have a problem of balancing comfort, flexibility, and protection. And next, also have a problem in retention and long-term durability. So how they overcome this challenge? Hybrid composite has been reduced in terms of their thickness and weight. Next, improve ergonomic panel design and breathable materials. And here are the advanced and innovation of composite armor in military. First one is nanomaterial enhanced composite armor. Recent research focused on incorporating carbon nanotubes (CNT), graphene and nanoceramics into composite armor materials. These materials significantly improve energy absorption, tensile strength, and crack resistance while reducing overall weight. So the impact they're given is higher ballistic efficiency than steel at a fraction of the weight. Next one is improved multi-hit capability. The second one is modular and adaptive armor systems. New composite armor systems are increasingly modular, allowing armor panels to be added or replaced based on mission threat levels. So the advantages that has been given to the militaries is reduce their vehicle downtime. Next, customizable protection for urban, desert, or battlefield environments. And lastly, lower life cycle costs. And the third advance and innovation is smart and adaptive composite armor. Emerging research explores smart armor systems, including shear thickening fluids that harden upon impact, embedded sensors to detect damage and impact location, lastly self-healing polymer composite under development. And number 4 is lightweight personnel armor innovation. So usually armor is very heavy and not comfortable to use. So for military and police use, they use advanced UHMWPE composite and hybrid fiber system that have led to thinner ballistic plates, improved mobility and endurance, and higher protection levels meeting modern NIJ standards. So this is criteria that make armor less weight and comfortable to use. And overall impact of advanced is modern composite armor now provides greater protection at lower weight. Next, improved maneuverability and survivability. And lastly, scalable mission-specific solutions.
I will sharing about benefits and advantage. First, composite armor provides strong protection while being much lighter than steel or metal armor. This allows soldiers and law enforcement officers to move faster, carry more equipment, and operate for longer periods without fatigue. Second, composite armor use a layered structure, while ceramics break the projectile and fiber composites absorb the remaining energy. This combination is highly effective against bullets, shrapnel, and blast fragments. Third, high energy absorption. Fiber materials such as Kevlar and UHMM WPE spread the impact energy over a large area. This reduces penetration and lowers the risk of severe blunt force injuries to the wearer. And last is design flexibility. Composite materials can be molded into different shapes and thickness. This allows armor to be customized for helmets, body vests, shields, and vehicle protection based on specific threat levels. And third explanation is about challenge and limitations of composite armor. First is high cost. Advanced materials such as ceramics and high-performance fibers are expensive. The complex manufacturing process increases production costs, limiting large-scale deployment. Limited multi-hit capability. Ceramic layers tend to crack after the first impact. Once damaged, the protection in the area decreases, making the armor less effective against repeated hits at the same location. Number 3 is thickness versus comfort trade-offs. To achieve higher protection levels, more layers are needed, increasing thickness. This can cause discomfort, heated build-up, and reduce breathability during long missions. The last challenge and limitations is difficult damage detection. Internal damage such as cracks or determination may not be visible externally. Armor that looks intact may already have reduced protective capability, requiring regular inspection of replacement.
Now, let's go through to the future trends. As of mid-January 2026, the composite armor field is accelerating toward lighter, smarter, and more adaptive systems. The NIJ standard 0101.05 is driving major redesigns. The first compliant products list, CPL, for .07 certified gear is expected early to mid-2026, while the old 0101.06 CPL will remain available through at least the end of 2027 for smooth transition. Manufacturers are focusing on RF1, RF3 rifle threads, improved multi-hit performance, better female fit designs, and stricter testing protocols. The industry outlook for 2026 is strong, with record growth in 2025 continuing into elevated defense budget, UHMWPE or ceramic, hybrids dominating, and innovations in nanomaterial and adaptive tech. The first one, we have extreme lightweight UHMWPE and Dyneema evolution. Next gen, Dyneema grades SB330 or SB332 for hard grades, SB301 for soft armor, enable 10 to 45% weight reductions. Rifle plates, RF1 thread, are now under 2 pounds. Some 1.65 to 2.2 pounds for 10 multiplied by 12, with thinner profiles and excellent multi-hit capability when baking ceramic. Second, we have nanomaterials boom, which is graphene and carbon nanotubes. Graphene-enhanced composites and CNTs delivered superior strength to weight, better energy dissipation, up to 50 to 100% gains in hybrids, and potential self-healing This enabled thinner, tougher strike faces with outstanding multi-hit performance, cross-section, and layer view of graphene integrated ballistic armor, which is in the picture here. Third, we have shear thickening fluids, STF, liquid or adaptive armor revival. STF fabrics stay flexible for comfort but harden on high velocity impact. Hybrids with UHM WPE are expanding for concealable soft armor, step or spike resistance, and better ergonomics in law enforcement and military soft balance. This picture right here is the impact test visual of STF-based flexible protection. Fourth, we have 3D printing, customization, and modular systems. Additive manufacturing allows custom-fit armor, articulate joints, rapid prototyping, and scalable modular carriers or helmets, which can reducing fatigue and enabling quick field upgrades. Futuristic 3D printed ballistic helmet and modular concept, which is in the picture right here. Last but not least, we have NIJ 0101.07, adoption plus smart and sustainable features. Full shift to 0.07 with unified threat catalog 0123.00, emphasize real-world threats. Emerging additions include embedded sensors for vital monitoring, dynamic response system, eco-friendly or recyclable composites, and multi-threat, which is ballistic plus agent protection. For conclusion, isomerism in coordination complexes and composite armor show how precise structural design shapes outcomes across scales. In chemistry, small differences in ligand arrangement determine a compound's properties and life-saving applications, as in cisplatin success versus its trans isomer. In armor, layered ceramic and fibers like UHM WPE provide strong protection with low weight, enhancing mobility for military and law enforcement. Together, they demonstrate that the right arrangement, whether of atoms or materials, turns weakness into strength and drive innovations that protect and save life in medicine with high-risk environments. That's all for our presentation. Thank you for watching.